networks, let's say we have random created networks in which the probability that a node has k neighbors is given by a function like this. Maybe you remember from statistics, this is a Poisson distribution. Okay, this is for random networks. Whereas for real networks, the probability that a node has k neighbors is given by k to the potent of gamma, where gamma means the degree exponent. And this is what we called a power law. Distribution. It's not a Poisson law, it's a power law, because it's to the power of gamma. The important factor gamma is going to be crucial in today's lecture. Okay, so definitions. Here, networks whose degree distribution follows a power law are called scale-free networks. You want your business to have a scale-free network topology because it has certain advantages that we have seen in the previous lecture. Okay. So scale-free network has following characteristics. Let's paint the two degree distributions in a graphic. Okay, this is the logarithm of the number of neighbors that a network has. And this is the logarithm of the probability that the nodes have k neighbors. Let's say this is 10 to the potency of 0, 10 to the potency of 1, 10 to the potency of 2, 10 to the potency of 3, and this is 10 to the potency of 0, 10 to the potency of -1, -2, -3, -4, -5, -6. So it turns out that the Poisson random network, say this, has this distribution. Okay, this is the, let me put it with color. This is the real, this is the real scale-free network, and this is the Poisson random network. Smaller than 0, there's like that. Okay. This is for a gamma value of minus of 2.1. Okay. And let's try to understand the meaning of these curves. Okay, there are 3 areas in this curve. First area, second area, and third area, given by the points where these curves cross. And let's try to discuss both of them, or all 3 of them. In this area, first, the random network has a smaller probability than the real network. So this value is smaller than this value, right? In this area. This red curve is under the violet curve. So for small values of k, number of neighbors The random network has a smaller probability than the real network. This indicates that a scale-free network, real, has a larger number of small degree of neighbors, of nodes, with few neighbors. Okay. The second area is the area for networks for degrees, number of nodes, of neighbors. Okay. In the area 2, the random network Poisson distribution is above the power law, indicating that in the random network there is an excess of nodes with average degree k. So in this area, here is the average degree. The Poisson random network has more nodes than the real scale network. Okay. And the important part comes now. Where we have a tail, it's so-called tailed, in the end, where the number of degrees comes to a higher number. So for degrees k that are large, the power law is above the Poisson curve. This difference is particularly visible in the curve. Okay, so here you see that this curve is way bigger than this one, which almost goes to 0, indicating that the probability of observing a high degree node or hub is several times bigger in scale-free networks than in random networks. So here, because the number of neighbors is very high here in this area, the probability of finding nodes with a lot of neighbors is higher in the scale-free network, in the real network, than in the Poisson network. Okay? So this is the interpretation of this, which means that in the real network, we find more hubs than in the random network. Okay? Questions, please? Klar. So, wenn die Anzahl, pass auf, wer hat gefragt, wie heißt der nochmal? Firat? Firat. So, pass auf. Die x-Achse ist jetzt die Anzahl Nachbarn der Knoten in einem Netzwerk. Okay, einmal 1 oder 10 oder 100 oder 1000. Okay? Wie viele Nachbarn ich habe. Und hier auf der y-Achse ist die Wahrscheinlichkeit, dass wir einen Nachbarn mit so und so viel, einen Knoten finden mit so und so vielen Nachbarn. Okay? Natürlich geht es maximal 1 bis halt 0, was Wahrscheinlichkeiten sind. Und dann hier, den ersten Punkt sagt aus, dass in der ersten Zone die Kurve der reellen Wahrscheinlichkeiten höher ist als die Kurve der Random Network. Das heißt, es gibt mehr Knoten mit wenigen Nachbarn in dem echten Netzwerk als in dem Random Netzwerk. Okay? Dann in der Mitte, also das ist der Mittelwert, gibt es mehr Knoten mit in dem Random Netzwerk, die ungefähr die mittlere Anzahl Nachbarn haben, als in dem echten Netzwerk. Und in dem echten Netzwerk gibt es die Wahrscheinlichkeit, Knoten zu finden mit sehr vielen Nachbarn, ist viel, viel, viel höher als in dem Random-Netzwerk. Das bedeutet, dass in dem echten Netzwerk sich Gruppen bilden von Knoten mit sehr vielen Nachbarn. Okay? Also sogenannte Hubs. Hubs sind Knoten, mit sehr vielen Nachbarn, with many neighbors. Okay? K sehr groß. Okay? Werden, you can find them in real networks. Werden gefunden in den echten Netzwerken. Okay? Knoten mit sehr vielen Nachbarn. Das wäre zum Beispiel ein Hub. Okay? Ist verständlich. Firat, ja, passt. Jo. Gibt es noch Fragen, bitte? Okay, what is the role of the degree exponent? Gamma in the network structure. So the properties of the scale-free network are going to be dependent on gamma. So first thing you need to know is that almost all real networks have a gamma bigger than 2. Okay? This is because in networks, information transmission takes time and energy. If we ever are able to make a network in which information transmission doesn't cost, then we will be seeing gamma lower than 2. Okay? If gamma is smaller or equal to 2, we find an anomalous regime. Okay, this means that the number of links connected to the largest hub grows faster than the size of the network. This means that for a sufficiently big network, so n tending to infinite, the degree of the largest hop must exceed the total number of nodes. This means that we will not have enough nodes in the network so the network breaks down to smaller networks. Okay, so the network is not stable and breaks down. This is for gamma smaller than 2. We have a problem with energy. Okay. For gamma between 2, bigger than 2 and 3, and smaller than 3, we find a so-called scale-free regime. This is the sweet spot. This is where we want to be. Okay? In this regime, the second order of the degree distribution, the second momentum of the degree distribution tends to infinite, as we have seen in the previous lecture. And as a consequence, organizational dynamics spread without a threshold. Okay, so this is the previous lecture. If gamma is bigger than 3, we find a random regime in this regime. The first moment of the degree distribution is finite. The second moment is also finite. So it exists, it's not infinite. This means it's not infinite. And as a consequence, organizational dynamics are not as robust as in scale-free networks. Okay, so I give you a summary table. And with this, we end the network theory applied to project management and process management. Summary table in which we have gamma, okay? Here we have number 1. Here we have gamma 2. Here we have gamma 3. And so on, okay? So the first thing we do is here we paint a line here, bam. And 2. And here we copy the line. Here, as we said, smaller than 2, k diverges, so tends to infinite. K squared tends to infinite. So not stable structure. The network cannot exist for long. Here, so this is anomalous. Regime. Here, k is finite. When k squared tends to infinite. So the average path length, as we saw the other day, is the logarithm of n, which means we have a scale-free network. This is, for instance, the World Wide Web, or these are the network of proteins in the human body, or this is the metabolic network of animals. I mean, there are many examples in nature. Here we have the situation in which gamma equals 3, okay? And for this case, we have an APL of logarithms of n divided by logarithms of n, okay? This is a scale-free regime. Anomalous regime, scale-free regime. And with gamma bigger than 3, we have our random regime. Okay, this is for instance, the citation network for papers or collaboration networks in projects in the industry. So here we have a k that is finite, and k squared is also finite. And here the average path length is proportional to the logarithms of n divided by logarithms of k. Okay? So when you find in the industry, in your future projects, when you have a network of a project, make sure the first thing you calculate is the average path length, so that you know if you are in a random state or if you are in a scale-free regime. Okay? So how do you know if you are in a random state or if you are in a scale-free state? Calculate the average path length. And depending on the value, depending on this value, you get different approximations of your position. Okay? Questions, please? Ja, gerne. Ich nehme die Vorlesung auf, ja. Wieso? Ah? Ich verstehe nicht. Die Vorlesung wird aufgenommen mit Hilfe von QuickTime und das iPad ist direkt angeschlossen an den Rechner. Deshalb vielleicht. Ja, das ist der Grund, warum ich nehme es jetzt, das kommt dann mit dieser Methode kommt in bessere Qualität, sowohl den Ton als auch das Bild, als wenn ich den iPad über WebEx anschließe. Und dann muss ich nur ein Gerät ans Internet anschmeißen und dann geht es schneller auch. Das ist der Grund. Ja, aber alle meine Vorlesungen werden aufgenommen und werden auch zur Verfügung gestellt, sobald die Vorlesung vorbei ist. Das mache ich jetzt so standardmäßig. Alright, Fragen bitte. Questions? Weil ich eigentlich krank bin. Ich weiß nicht, ich glaube, ich habe es gesagt in der Vorlesung. Ich möchte jetzt nicht über Internet streamen, welche Krankheit und so, aber ich werde nächste Woche operiert. Und ja, eigentlich könnte ich mich krank schreiben. Ich könnte mich krank schreiben und dann keine Vorlesung halten, aber ich kann die Vorlesung im Sitzen halten. Stehen ist suboptimal und ich halte es einfach nicht aus, deshalb ist es online. Aber, ja, danke. Ich dachte, ich hatte es letzte Woche gesagt, oder? Aber stimmt, letzte Woche war Urlaub. Ja, genau. Ab nächste Woche gibt es dann, also ab dem 17. gibt es dann keine Vorlesungen mehr dieses Jahr. Deshalb ziehen wir Stunden vor oder nach. Ja, das ist der Grund. Wie gesagt, ich muss unter dem Messer nächste Woche und das wird dann dementsprechend ja, nicht so toll. Mal sehen. Ja, so sieht's aus. Ich hoffe, dass wir uns im Januar fortsehen können. Ja, noch Fragen bitte? Wie gesagt, ich könnte mich krank melden, aber das wäre scheiße für euch, vor allem im 7. Semester, wenn jetzt die ganzen Vorlesungen ausfallen. Deshalb machen wir das jetzt so gut wie es geht. Okay, then we continue with some theory, because as I said, I'm done with the network theory. Now we look at some more management theory, and this is agile project management. This is something that is very, let's say, on right now in the industry, so something that might be interesting for you to learn and internalize well. These concepts, independently of the exam, agile project management is something that you might be looking at face to face later on as a project manager. Okay. So the thing is, the first question is, what is agile? Okay. Now this is something that it's some sort of a definition. Okay. This is a project management method that uses short development cycles called sprints to focus on continuous improvement in the project or process or product. Okay. So this is a definition. We look at short continuous improvement cycles, or so-called sprints. Okay. It was developed by Google, and we have what they call 12 keys of agile projects. It's the project management method by Google. It's kind of interesting to see how they work. Okay, they base it in 12 elements. The first one, this is something that could be asked in the exam. Okay, just the first one is to focus on customer satisfaction. Okay, always the first priority. To start always with the customer. Okay, we look always to focus on reducing lead time. In German, wir wollen immer die Durchlaufzeit reduzieren. Okay? After focusing on the customer, then we try to, here the focus is on the lead time, then we focus on flexibility. Okay? So changing environments or conditions are welcome and embraced at any stage to provide the customer with competitive advantage. Here we focus on our KPI on EPI. Every part, every interval. We will look at these KPIs in detail next week. Okay, this is related to the third focus, which is frequent delivery. Frequent delivery. We want our service to be delivered on demand with frequent delivery. So this means we are focusing on the Umschlaghäufigkeit, or the turnover rate. In German, Umschlaghäufigkeit. So you see, I'm giving you KPIs that are relevant for each stage, and this is going to be very important later on for it's going to be important for the next class. Okay, so next week. So the next one is to focus on collaboration within the network. So here we focus on average path length and clustering coefficient. Okay, we know that these two KPIs, we have seen them in the past. So the fifth is we focus on the leadership framework. Here all team members remain motivated for optimal project outcome. Okay. Here the focus leads on trust. How to measure trust, it's crucial, and it's not easy. Okay. The number six. So can you follow? Or am I too fast? Sorry. So here we have face-to-face meetings. So basically what they say is that meet people in person, meet people in person is better than telephone, is better than email. Okay, and this goes for online meetings. So whenever you can, try to perform a conference call instead of telephone or just email. So how do you define success of the process? Definition means success means that the product works for the customer. Okay, and nothing else. That's the only thing that matters. Number 8, Feel free to interrupt me if you have any questions. Nicht das auf Deutsch erklären sollte, wie auch immer, okay? Sustainability. Nachhaltigkeit ist wichtig. Sustainable development. Is accomplished through agile processes, whereby development teams and stakeholders are able to maintain constant pace. Okay, so no strain on the people. It's important. If you strain your people, you can do it for a short period of time, but you break them and then you lose them for a longer period. So focus on excellence. What excellence means, I give you the best possible, in my opinion, definition of excellence is the next 5 minutes. So if you want to be really excellent in your communication, in your work, focus on your next email, focus on your next 5 minutes of interactions with all the people. If you don't know the names of the daughters and sons of your workers, you have not tried hard enough. Okay, so focus on the next 5 minutes. Be excellent with your people, and they will be excellent with your customers. Focus on simplicity of design. Some people say, keep it simple, sister. Okay. Try to create self-organizing networks or teams. This means make them scale-free. How do you get scale-free? With your average path length, similar to the logarithms of n, and a very small clustering coefficient. No, a very high clustering coefficient. Those are the conditions. Okay. And the last one, we will talk about that next week. Create regular intervals of communication through so-called shop floor management. This is a super important issue. You will be knowing about that when you start working. Okay, so here we focus on regular intervals of communication. They're going to be, or the example I'm going to give you, it's going to be based on the CPDNA. Make sure you review that. And the so-called DCPNA, one is for process, one is for project management. you can find that information in the previous lectures. Okay, we will see examples of this as of next week. Okay. So these are the 12 keys for project management. Questions, please. So the roadmap, this is the last point today. The roadmap for agile project management. Let me give you a little roadmap. Can be put like this in, let's say, 6 steps, 7 steps, I guess. First one is to create the team. Okay. Create your team, which is going to have, as we have seen before, network structure. Okay. It's going to be focusing on the goal. You're going to try to develop the team with a low average path length and a high clustering coefficient. Okay. So the second step is to create a project backlog. This is nothing but creating a number of sub-activities to break down the goal. So the goal is broken down in a number of activities that need to be performed. The goal is broken down into parts. Okay. The third step is to create a time frame. Put all these goals and in that are or sub goals that are coming from the backlog into a time frame. Okay. So all these activities need to go into a time frame. Then you create the so-called sprint backlog, in which you review with short cycles the progress. And this is done with CPDNA or DCPNA. Okay. And then you perform some iteration loops. Every on the CPDNA or DCPNA, every time intervals, depending on the hierarchical level. As we will see, this is called shop floor management. The last part is to standardize through best practice sharing. This is the ACT part of the CPD NA or DCPNA. Okay? Until you achieve the goal, which is achieved, as we said, when the customer gets what they want. They get a working solution. Okay? Questions, please? All right, then let me stop a second.